What if you could bring the minds of Plato, Aristotle, or even Alan Turing back to life inside a video game? Well, welcome to PhiloAgents, the first open source course that will teach you how to build an AI agent simulation engine that brings historical figures to life inside an interactive game environment. There are many YouTube videos and tutorials out there that teach you how to build AI agents. But with this one, we wanted to create something that is closer to a real-world or production-ready application. That's the reason why we will teach you how to build robust memory systems using MongoDB, how to build complex agentic workflows like agentic RAG using LangGraph, how to use fast LLMs using Groq as the LLM inference provider, how to deploy your agentic application inside FastAPI, and how to use Websockets for real-time communications, and lastly, how to apply LLMOps for agent observability. But before we dive in, I wanted to introduce you to the co-author of this course, Paul Justin. So Paul, whenever you're ready, man.
Hello everyone, I'm Paul Justin, the co-author of the PhiloAgents course, where I contributed to the code and the written lessons of the series. So I think this is one of the funniest ways into getting into AI agents and learning about AI agents. I have 8 years of experience in software engineering, AI research, AI engineering and MLOps, and I poured all this knowledge into this course, where the most exciting part of it is that we manage to show you how to build and architect an end-to-end AI system. This is important because in normal production-ready AI products, usually the algorithm, the AI, the agentic part is just like 10 to 20% of your system. The rest consists of other components that are used to ship your system to your users, to make it reliable, to make it consistent, and so on and so forth. So in this course, along showing you how to build the actual agents, the actual PhiloAgents, we will show you how to wrap everything into a backend front-end architecture. More exactly, we will ship the agent as a RESTful API and hook it to this game UI, which gives you this PhiloAgents experience. And also we will show you how to add an observability layer, which is part of MLOps, and ultimately how to wrap up everything in Docker containers so they're actually shippable to cloud vendors such as AWS or GCP. So yeah, there's a lot more to this course, but I will leave the rest to Miguel. And I'm super excited that you're viewing this course, and I hope you will have the chance to learn a lot and have fun. Yeah, so bye.
Thanks, Paul. So now let's see what we will be covering during this course. Lesson 1 is going to be about the general architecture of the PhiloAgents application. We will talk about the API and the UI. We will talk about the different components that compose this application and the different providers and tools that we are going to use to bring all the philosophers to life. Lesson 2 is going to be about LangGraph and how to create complex workflows like agentic RAG using this framework. Lesson 3 is going to be about memory, and we will see how to implement short-term memory and long-term memory using MongoDB. Lesson 4 is going to be about FastAPI and how to deploy your agentic systems behind a FastAPI application. You might be used to the HTTP protocol. Well, in this case, we will introduce you to the WebSocket communication, because you will see how to implement this real-time communication between the game UI and the API, the agentic API. Lastly, in Lesson 5, we will see how to apply LLMOps to the PhiloAgents project. You will see how to do agent monitoring and observability, how to do prompt versioning, and how to run evaluation on your RAG system. And that's everything. I really hope you enjoyed this course, and I hope you learn a lot of things out of it. But if you're ready, let's begin. This is not a traditional video game, and these aren't your regular NPCs. Each character you see on the screen right now is actually an AI agent pretending to be a historical figure. Plato, Aristotle, Turing, all of them are simulated by a complex agentic backend. A simulation where ancient philosophy meets modern AI. In this practical course, you will build an AI agent simulation engine that brings historical philosophers to life in an interactive game environment. Imagine having deep conversations with Plato, debating ethics with Aristotle, or even discussing artificial intelligence with Turing himself. And all of this while you learn how to build AI systems that actually work. Ladies and gentlemen, welcome to the Neural Maze. Hey guys, welcome to lesson 1 of PhiloAgents. In this first lesson, I'm just going to give you a very high-level overview of the architecture and all the tech stack that we will be using throughout these 6 lessons. But before I begin, I want to give you a quick introduction to the 5 additional lessons that we'll be covering in the next 5 weeks. Lesson 2 is going to be about creating a PhiloAgent. This is the name of the philosopher agents that we have created. And we are going to create these PhiloAgents with LangGraph. LangGraph is going to be the agentic framework that we are going to use to generate all the agentic workflows. Okay, in lesson 3, we are going to cover the memory system. As you remember from my previous videos where we implemented this WhatsApp agent, we used SQLite and Qdrant for creating these memory systems. In this course, we chose to use MongoDB as the memory system. We are going to store both the short-term memory and the long-term memory in this popular database. In lesson 4, we are going to cover the agentic API implementation. All right, that is, we are going to take all the agentic workflow and expose this agentic backend from a FastAPI application. And we are going to also implement WebSocket, which is going to be really cool because this provides a very good way for the communication, the real-time communication between the video game and the agentic backend. Okay, we are going to cover WebSockets, as I was saying. In lesson 5, we are going to evaluate agents, that is prompt monitoring, prompt versioning, and observability using Opik for that. And in lesson 6, we will see how everything works together, how all the different pieces work together in this multi-agent simulation. All right, so now let's go to the next slide where we have this high-level architecture that I believe simplifies a lot the understanding. Okay, so let's start isolating different components here. You can see in yellow here, this rectangle in yellow. This signifies that it's the online part. All right, this rectangle is encapsulating all the different components that belong to the online phase of the PhiloAgents project. Okay, the online phase is basically the moment where you start interacting, you start playing the video game, and you start interacting with the agents in real time. All right, but then we have an offline phase, all the things that are outside this rectangle. All right, so we have all of these data sources, this generate eval dataset, etc. We are going to focus first of all in this offline phase. So this RAG feature pipeline that you see in here is necessary because we are creating philosophers, and every philosopher, every thinker, Turing, Ada Lovelace, Socrates, Aristotle, they have a very specific context, a very specific way of seeing the world. For example, Plato will believe in some ideal forms, or Socrates will believe that there is an ideal justice. Turing will be focused on the Turing test and the Turing machine and how to explain computation. So all of this information, all of this context is going to be fetched, is going to be retrieved from Wikipedia and also from the Stanford Encyclopedia of Philosophy, which is one of the top authorities when it comes to philosophers and thinkers. All right, we are going to retrieve all of this data, all the relevant information for each one of the philosophers from Wikipedia and from the Stanford Encyclopedia of Philosophy, and we are going to store that into MongoDB, that is into this long-term memory. all right? Going to take all of this information, we are going to transform this information into embeddings and just put everything into the long-term memory, all right? Because then, during the online phase, we will be retrieving information from this MongoDB instance. Perfect. Of course, this is something that we are going to cover in much more detail in lesson 3 when we cover the memory systems, but just to give you a very high-level overview. All right, so that's exactly the goal of this RAG feature pipeline, all right? That creates this vector index inside the long-term memory. All right. This generate eval dataset is also very important because, as you might know, many people build RAG systems, but only a few are evaluating these RAG systems. And we need this generate eval dataset for that exactly. We need to create a set of questions for Plato, a set of questions for Socrates to really be sure that our RAG system is working as expected, all right? And this is something that we are also going to cover in lesson 4 when we talk about observability, pro-monitoring, and evaluation, all right? Perfect. You can see, by the way, here that Opik is mentioned because we are going to treat all the evaluation, all the pro-monitoring, etc., the observability with this amazing tool, Opik, and MongoDB that I have already mentioned. So for the online phase, what you need to understand is that we have two main components interacting with each other, all right? We have a game UI. This is implemented using Phaser. Phaser is a framework, a JavaScript framework that lets you create or implement video games that are running in the browser, all right? Like in Google Chrome or whatever. And that's exactly what we have built. We have built an interface, the PhiloAgents town that you saw at the beginning of this video with Phaser 3. And that's this module that you see here, this game UI, all right? And when you interact with any of these philosophers inside the game UI, you are going to interact under the hood with this agent inference pipeline or agent backend, all right? So let's see what are the different components that build up this agent backend. So first of all, we have this FastAPI server. This is the API that Phaser is going to interact with when you start talking with a philosopher. Then the FastAPI server is going to connect with the agentic layer that you can see here that connects all the LangGraph related code that defines the agent workflow. All right. And the agentic layer is going to connect as well with everything related to the state client. This means the graph state client, okay, that it's going to be persisted inside the short-term memory in MongoDB. The retrieval tool, this is necessary to retrieve the information that we have previously stored using the RAG feature pipeline. Prompt management, we have a lot of different prompts that we also need to version, we also need to use inside the agentic layer. For example, the character prompt, the summarization prompt, etc. And then the LLM gateway. And in this case, we are using Groq as the LLM provider, as you can see right here. In particular, we are using Llama 3.3 70 billion for all the interactions that you see inside the game UI. And we believe Groq is a very good choice because it provides a very generous offer in terms of the number of tokens that you can use. And and it's great that you can be using powerful LLMs like Llama 3.3 70 billion for free. I mean, that's amazing. Okay, and I think that's basically it for this general introduction to the architecture. Now I'm going to show you one last slide where I'm going to give you an additional way of looking into this. So here you can see that there are three main components, and then the LLM API. This is the LLM provider. We have the server, we have the memory, and we have the game UI, all right? So what's going to happen? Let's follow the numbers here. So we have here 1. Suppose that you or Sophia, we call the character Sophia because it makes sense, we think. And she's speaking, or you are speaking with Turing, all right? So when you send one message, when you say to Turing, hey, how are you? I know you are Turing. Pretty cool idea, you know, the machine, the Turing test stuff. All right, so what's happening is that this question, let's follow the path of the question, is going to reach the agentic layer. And in here, we are going to, let's move to the previous one. It's going to pass through the FastAPI server, the agentic layer, and with all the LangGraph workflow that we have implemented and that you will see in lesson 2, we are going to provide an answer, all right? Of course, here in 6, this agent is going to make use of a tool in case the agent needs it. If we are asking about a specific topic of Turing's context, like for example, hey, tell me everything you know about the Turing test or the Turing machine. In that case, it will make use of this tool right here. And it will take all of that information from the long-term memory, all right? Because remember that we stored all the context about Turing as embeddings inside the vector database, MongoDB, the vector search capabilities of MongoDB. Perfect. After that, after the agent has processed all of the information and generates a response, the response is going to be sent back to the game UI. And that's exactly what you will see as Turing responding. All right? We think both this architecture, this diagram, and this diagram make a good introduction to what we are going to build. So now that you have a mental map of what we are going to build, I think it is time to move into the repository. I will show you how to clone the repo, although that's trivial, and how to set up everything to have your own PhiloAgent simulation running locally. So let's go. All right, so you need to go to the Neural Maze organization in GitHub, and in there you need to look for this repository PhiloAgents course that you can see right here, PhiloAgents course. So you get inside, and what I'm going to do first of all is just to clone this repo. Yeah, let's open a terminal here and let's go to desktop, for example, and simply clone the repository. And now let's get into a repository, and we are going to open a cursor IDE, but you can use whatever IDE you want. So let's get inside. It's called PhiloAgents course. Okay, and now we are opening cursor in this folder. All right, so when this is ready, okay, let me put the cursor tab here. All right, perfect. You will see something like this. You have the VS Code with all the parameters, and then 2 core components that are basically the PhiloAgents API, that is the agent backend that I've been covering in the previous slides, and also the PhiloAgents UI that contains the game UI. If you get inside the PhiloAgents UI, for example, you will see that it is in itself a phaser project containing a lot of code related to the classes, the different classes that are going to be part of the game UI, the scenes, all the different scenes like the game scene, the main menu scene, etc. Everything in JavaScript, and all the different services for the API connection with the agentic backend. All right. This is for regular HTTP requests, and this is for the WebSocket connection that we are going to cover when we implement all the FastAPI application. All right. Let me know if you want some deep dive inside this JavaScript code, because our main idea, our initial idea was that this course is for AI engineers and ML engineers that want to understand way better how to implement agent applications, real-world agent applications. So we thought that we could take for granted all the JavaScript code. But of course, if you want some bonus lesson where I explain all the different classes and all the JavaScript code that I have implemented, then let me know in the comments, and of course I can do it. But yeah, this is the PhiloAgents API UI that contains the game UI, and then we have the PhiloAgents API, all right? And this is in itself a Python project, all right? You can see here that has the PyProject YAML. It has a Docker file if you want to containerize all this Python project, the env example, Docker ignore, and notebooks, the data that we need for the evaluation dataset. And here inside the source PhiloAgents, you have the proper application, the proper PhiloAgents application, and it's structured with using clean architecture. Okay, you can see here the application layer, the domain layer, and the infrastructure layer. But of course, I will cover each one of the components of these three layers in later lessons. All right, so don't bother about it. In this lesson, I just want to be brief and just show you how to set up everything to have this running on your local laptop. So to start using PhiloAgents, you will need to go to this install and usage markdown that contains basically what we need. So let me show you how you can do it. Okay, let's close down the original one and let's get started. So here in the install and usage, you have all the prerequisites that you need, like UV, the version of Python, Git, Docker, okay, things that I assume you already have on your local machine. And if you keep scrolling down, you will see all the different steps that you need to take to have PhiloAgents running on your local laptop, okay? So we have already cloned the repository. Oops, sorry for that. We have already cloned, as I was saying, the repository. And what we need to do now, let's open a terminal. What we need to do now is to get into the PhiloAgents API, all right? Inside this API, inside this folder, we are going to create, first of all, a virtual environment, all right? You can do it like this, and we are creating a virtual environment just inside here, all right? The PhiloAgents API folder. After that, we are just activating this virtual environment. We can do it with source.env vim activate, and you can see that the virtual environment is already activated. And after that, we are just going to install all the dependencies, all right, which are quite a few for this project. All right, so we are installing everything that is needed for PhiloAgents to run, and lastly, we are just going to run this this command to test that we have Python 3.11. All right, so uv run, and now Python, and we are going to check the version. And after a bit, we will see that, yeah, the Python version install is 3.11.9. So now it's time to take the environment to set the environment variables, okay? And to do that, we just need to copy the env example that we have provided in the repo and just create another env with the proper environment variables that we need, all right? If we go inside, you will see that we just need 3 of them for this to work. We need the Groq API key. We need the OpenAI API key. This is necessary for module 5 because Opik works with OpenAI, just with OpenAI, and that's the reason why we needed this. And lastly, the Comet API key, all right? You might be asking, why don't we need, for example, all the connections with MongoDB? Because if we run this locally, and that's my aim in this first lesson, you don't need any connection, any password, anything to get the connection with the remote Atlas service, all right? I will leave you a couple of minutes to take all the relevant environment variables and to put them in the .env file, and after that I will show you how to start the PhiloAgents project. Okay, so if you have everything installed, it's time to start PhiloAgents on your local machine. Okay, so you need to go to the previous to the parent folder and then just run make infrastructure app, all right? That is going to start the 3 services that we need for PhiloAgents to run, all right? By the way, if you go to the Docker Compose, you will see the 3 services that I'm referring to. First of all, we need this local dev atlas, the MongoDB database for both the short-term memory and the long-term memory. Then we have the API, that is the agentic backend. And lastly, the UI that contains the game UI that is going to start the phaser application that we have defined inside PhiloAgents UI. And now this Docker Compose is going to run. And if we go in fact to Docker Desktop, you should see here like the containers spinning up in a few seconds. So let's see how it goes. It's going with the API, creating the API backend. All right, so here it is, PhiloAgents course application, and it contains the 3 services that I was telling you about: PhiloAgents UI, the MongoDB database, and lastly the PhiloAgents API. Okay, so Since this is just an overview video, I'm just going to show you how to interact with the video game itself. So just click, let's go to localhost 8080, and you should see something like this. This is the PhiloAgents UI. So you have three options. First of all, you have these instructions: arrow keys for moving, space for talking to the philosophers, and escape for closing the dialogue when you're speaking with one of the philosophers. Of course, you can go to support us by giving a star to our project. And then we have the let's play button, which I think is the interesting one, right? So let's play, and you can move Sophia with the arrow keys. I tried to give the philosophers some kind of historical coherence. So first of all, you'll have the Greek philosophers: Socrates, Plato, and Aristotle. For example, here, hello, who are you? And you can talk with whoever philosopher you want. So I am Plato, seeker of truth and wisdom. I invite you to join me on the journey through the realms of thought. So very boring, Plato. Here we have Aristotle in that garden. Here is Descartes. Hey, what do you think of the phrase, I think, therefore I am? Sorry, I'm a bit nerd with philosophy, as you can see. So, bonjour, I am René Descartes. That phrase, je pense donc je suis, my French is terrible, is my own. A conclusion I reach after doubting everything, even my own existence. But tell me, can you truly think? So here, for example, that I'm asking about specific ideas or philosophies of the specific philosopher of Descartes, in this case, it's going to use the tool to provide relevant context from the RAG system, all right? Okay, we keep walking through the village. You see here Leibniz and also Ada Lovelace. Here we have John Searle and the famous Turing here. So, hey, what is a Turing machine? Alan Turing. A Turing machine is a mathematical model for computation, a simple device that reads and writes symbols on an infinite tape, helping us understand the limits of computation and decide a machine can truly think. That's beautiful. Let's look at this. So, can a machine fool you into thinking it's human? I don't know. Okay, you can see how you can interact with all of these philosophers. They are going to start asking you about different topics, about what is consciousness, what is AI, the ethics of AI, etc. Depending on each one of the philosophers, the topics are going to be very different. All right, so here we have Turing, Dennett, Chomsky, Noam Chomsky, and lastly, two great philosophers from the 21st century, Miguel and Paul. All right, and you can talk to both of us. So, hey, we will always give you the same answer. So, hey there, I'm Miguel, but you can call me Mr. Agent. I love to chat, but I'm currently writing my Substack article for tomorrow. If you're curious about my work, take a look at the neural maze. And the same goes with Paul here. Yo. Hey, I'm busy teaching my cat AI with my latest course. I can talk right now. Check out the coding mail for more of my thoughts. Okay, so just a funny Easter egg in the video game. All right, and this is everything for today. I hope you enjoy playing with PhiloAgent simulation. And yeah, let me know in the comments what you think about it. Next week, we will cover how to create these AI-powered NPCs using LangGraph workflows. And until that time, happy coding. Hello friends, welcome to PhiloAgents, the interactive simulation where agentic AI meets philosophy. You will get the chance to speak, to chat with different historical figures from Ada Lovelace, Leibniz, Descartes, Dennett, Turing, Plato, Socrates, etc. Each one of the characters of the NPCs that you see right now are actually AI agents pretending to be these historical figures. And the way that you interact with them is pretty simple, as I will show you. So let's move Sophia. Sophia is the main character, the one that you will control. And let's start talking with Turing, for example. So let's press the space button and hello, my name is Miguel. I'm Alan Turing. I'm intrigued by the notion of thinking machines. Can a machine truly think or just mimic human thought? So each one of these philosophers is going to ask you about AI-related questions. Socrates, for example, will ask about the ethics of AI. Turing will ask about the Turing test, Turing machines. So what I want to show you today, what I want to explain today, is how you can build these NPCs with a LangGraph workflow. Or to rephrase this, how you can build the brain of these AI, of these intelligent NPCs using LangGraph as the agentic framework. Okay, so okay, this is Turing saying his stuff. I think he asked about if machines can truly think. So let's say, I don't know, but I've heard of the Turing machine. Turing machine, my theoretical model for computation. Okay, so now if we go to comment to Opik, this is the tool that we are going to use for all the observability and evaluation on observation of agents, and we are going to cover this in lesson 5, but I just want to give you a very quick glimpse of the appearance of the LangGraph workflow that we are going to use. By the way, here in Opik you have a lot of amazing information, like the different prompts that you're going to use, correctly version. For example, here you have the philosopher character card. This is the template prompt that is going to define the system prompt for each one of the philosophers, like the personality. We also have data sets in case we want to use a data set for evaluation, which in fact we are going to do in future lessons. And here inside projects, if you click PhiloAgents, you will see that we have these traces. This is really interesting for what I want to show you right now. Click here, for example, and you can see that this is the last message that is sent to Turing, right? Like, I don't know, but I've heard of the Turing machine. And after that, Turing will respond with the Turing machine, my theoretical model for computation, but I've also proposed blah, 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 all right? This is the traces, but what I want to show you is the agent graph, because this is exactly how the brain of this PhiloAgent, Turing PhiloAgent, actually works. We will see this in LangGraph Studio, but just to let you know that today's video is going to be covering each one of the nodes, of the edges, and the agentic graph that maybe you are not seeing right now, but I will explain it to you. The agentic graph that takes place in this LangGraph workflow. All right? Okay, so before we begin, I just want to give you a very quick reminder, and this reminder is that you have all the code already available inside the PhiloAgents course, all right? You can go here and you can follow all the different instructions that we have put in the install and usage markdown. And in there, if you follow each one of these steps, you will have your own version of PhiloAgents running locally on your machine. So yeah, that's exactly what I have done. I've created all the environment variables, etc. And after you run this command, this make infrastructure app, you will be able to start playing with the game as I did in here. All right, perfect. So let's go then to the repository, not to the repository, to the IDE, to Cursor. And in here, I just want to explain to you some of the directories and of the folders we are going to cover. So first of all, in terms of the UI that you have seen when you go to one of these agent NPCs and you start talking, what's going to happen here is that when I press the space button and I start typing my question to the philosopher, so you're going to interact with one of several, not one, several classes inside the PhiloAgents UI, the user interface that we have implemented using Phaser. Phaser is the JavaScript framework for browser games that we have used for this project. So the classes that interest me the most are, first of all, the dialog manager. This is the class that manages all the interaction between the philosopher and yourself using the dialog box. Okay, by the way, you have this dialog box in here, which defines all the different UI components for creating this this dialog box, basically. And then we have the dialog manager that controls all the interaction with the agentic backend. Okay, it will control the active philosopher, the one that you are talking to. Like for example, in this case, the active philosopher will be Cyril, And also it's going to process the WebSocket message. Remember that in this project, we are going to interact, the Phaser application is going to interact with a FastAPI using the WebSockets protocol. All right, perfect. So apart from that, apart from the dialog manager, you can see here that it's processing the WebSocket messages, handle the default message in case there is not WebSocket return, etc. We also have inside services, this WebSocket API service. All right, and you can see here that it's going to connect with the localhost and port 8000, and this is exactly the point or the place where we are going to deploy. Let me show it here. We are going to deploy our FastAPI application. All right, you can see it's in localhost and port 8000. In fact, you can also access here the Swagger. Yeah, so here you have the FastAPI that the Phaser is going to interact with. All right, okay, so now that you have a very general grasp of what is happening, that is when I start talking with Cheryl, for example, a WebSocket connection is going to be established between Phaser and the FastAPI application, and we are going to send this Joe. All right. After that, what's going to happen is that this Joe is going to be received by the FastAPI application, and the FastAPI application is going to take care of taking the graph, the LangGraph workflow, and generating a response using this workflow. And after that, we are going to return the response using as well WebSockets. And this is exactly what you have here. I'm George Searle. Nice to meet you. I've spent years pondering the nature of understanding, etc., etc. All right. So now that you know how it works in terms of the UI, this WebSocket connection, this WebSocket API service, I'm going to show you what it looks like in terms of the agentic backend. All right. And to show you that, first of all, let's go into source PhiloAgents infrastructure. Okay. Inside infrastructure, you will see this API.py. The API.py is going to define, first of all, this HTTP endpoint chat, and also this WebSocket chat. That's the one that we are going to use. And I'm not going to get into the details of this WebSocket syntax, but what I want you to check is this part over here, this get streaming response, because this is the function that is going to call the LangGraph workflow. All right. Previously, of course, we are defining some abstract classes, some internal domain classes that we need for the philosopher. Let me show it to you very quick. So we have this philosopher factory module that contains the relevant information we need to correctly impersonate with an agent the historical figure. All right. So let's take, for example, Turing. That's the one that we chat with at the beginning of the video. So we have Turing. Here we have like the philosopher name and the translation between the ID and the name. On Turing, then we have the philosopher style. What is the style that Turing is going to use when it connects, when it interacts with you? For example, Turing analyzes your idea with a puzzle solver's delight, turning philosophical AI questions into fascinating thought experiments. He'll introduce you to the concept of the Turing test. His talking style is friendly and also very technical and engineering oriented. All right, so this Turing's style, and also philosopher perspectives. The Turing's perspective about AI. Here, in this case, you can see Turing right here. So Alan Turing is a brilliant and pragmatic thinker who challenges you to consider what defines thinking itself. Proposing the famous Turing test to evaluate AI's true intelligence, he presses you to question whether machines can truly understand or if the behavior is just an imitation of human cognition. That's exactly what Turing asked us about, right? Perfect. So with all of this information, we are going to use the philosopher factory to create philosopher classes, philosopher objects, to be more precise, right? You can see here that we are creating this philosopher class, right? It's pretty simple. I mean, it's just a pydantic base model that defines the ID, the name, the perspective, and the style. And all of this information is going to be encoded inside the character prompt. The prompt that we are going to use to simulate the personality of each one of the philosophers. By the way, you have it here inside prompts. Okay, we are using Opik, as you already see, for versioning each one of the prompts. We believe this is very good in terms of software engineering best practices, and this is something that many people overlook, but it's necessary to version all the prompts. I mean, here you have the philosopher character card, okay, that's going to take the philosopher name, the perspective, the philosopher style, etc. And it's going to use this to create the system prompt for all the interactions with the philosopher. Okay, perfect. Right, so now that we know how this philosopher factory works, it's going to generate this philosopher object. All of this information is going to be passed to this get streaming response. It's going to use the LangGraph workflow to generate a response and return the response using the WebSocket protocol. You can see here, right? Like await, WebSocket send JSON, and then for each one of the chunks of the stream, we are going to send the response to the UI. That's exactly what we saw when Turing, also Searle, responded to us. Perfect. So let's continue and let's get inside the get streaming response. Inside here, you will see that first of all, we are defining the workflow graph. This is what we are going to look, but first of all, let me show you how this graph is going to be called. We are defining the checkpointer. Remember that we are checkpointing the LangGraph state inside MongoDB. This is what we call short-term memory in a fancy way, and we are going to cover that in a future lesson. We are going to cover both the long-term and the short-term memory, but just to let you know that this is basically it. I mean, we're just going to take the LangGraph state and we are going to persist this state inside MongoDB. All right, and that's why we need this checkpointer. After that, we are just compiling the graph using this graph builder compile with using the checkpointer, and then we are just using the Opik tracer to get all the traces that we saw. Remember that if you go to comic Opik, you will see here all these traces about the different chains and the different pipelines that are being called. Okay, after that, we are just defining the thread ID for the short-term memory. This is something that we will cover in future lessons, as I was saying. And lastly, we are just streaming the result using this LangGraph method for the graph stream, asynchronous stream. Okay, and we are passing all the relevant inputs for the graph computation. So now that you know how this is going to work, all of these chunks are going to be returned, remember, using this API, API WebSocket connection to the UI. Now that we know how this is going to work, it is time to see how the workflow, how the graph actually works, how it is implemented. And to do that, I'm not going to rely on the Opik graph visualization. I'm going to do something that I believe is more easy to understand, and that is to use LangGraph Studio. All right. To do that, just verify that you have this LangGraph JSON in your version of the repository. This is something that I've just pushed a few hours ago, so just make sure that this is on your repo. And if this is on your repo, then you can simply install LangGraph Studio and just open LangGraph Studio inside the PhiloAgents API folder, all right, inside here. And if you do that, you will have something like this. This is the UI that will be open to you. And this is a very nice depiction of the LangGraph workflow that we are going to be using whenever we interact with whatever philosopher you want. So as always, when we use LangGraph, we have this start node. We need that because that's the node that indicates that the LangGraph workflow is going to start at that specific point. And then we are getting into this conversation node. So now we are going to be pivoting between this visualization and also the cursor code, because I think it's going to be easier for you to understand. So the conversation node, you can see here that the conversation node has two arrows, outbound arrows, right? One of them is going to link the conversation node with the retrieve philosopher context, and the other one is going to link the conversation node with the connector node. This connector node, by the way, is a dummy node that's just going to allow us to connect, but it's transparent in terms of computation, right? It does not perform any kind of computation. Okay, but I will show you later in the code. So the conversation node is going then to connect using the connector node with both the summarized conversation node and also the end node. but it's also able to connect with a retrieve philosopher context. Of course, these dotted lines in the links in the edges signify that we are talking about a conditional edge. And what is the condition behind this conditional edge, you might be asking? It's basically the agentic rack, because in this conversation node, the agent is going to decide, okay, do I need to fetch some relevant context and relevant data from the historical context? Remember that all of this data was fetched from Wikipedia and the Stanford Encyclopedia of Philosophy and was stored as embeddings, of course, inside MongoDB. That's the long-term memory that we are going to cover in future lessons. But yeah, as I was saying, this conversation node is going to decide, okay, do I need to get relevant embeddings, relevant context from that vector database from MongoDB? That's the retrieve philosopher context. Or should I just return a simple response? All right. In fact, if we go to Opik again, you'll see here that we are receiving basically a normal response. I mean, we are not going to fetch any relevant information from MongoDB, because in that case, we will see that the agent is using a tool, the tool rack. All right. But let me show you what happens if I ask Cheryl, for example, about the Chinese room argument. Can you give me relevant information about the Chinese room argument? And if we ask this, you will see that, if we go to comment again and we click this link, you will see here that there is something additional, something that didn't appear in the previous trace. That is the retrieve philosopher context. Our agent, NPC, is using a tool. It's using this tool to retrieve relevant context from the MongoDB long-term memory, okay? That's exactly why we needed agentic rack, because when we said something so stupid as Cheryl didn't have the need to retrieve any relevant content from MongoDB. But when we ask about a specific information that we really want to know, in that case, the agent is going to say, okay, I really need to get this relevant context, this relevant information from the historical context that I have stored inside MongoDB. All right, and that's exactly why we need agentic rack. Hope this is clear. If you have any additional questions or you want me to get into more detail in the future videos about the agentic rack, then just let me know in the comments. Okay, so that's basically the conversation node. And this pipeline over here is the agentic rack. We are going to retrieve the philosopher context, like Cheryl has already done when he retrieved all the context from the Chinese room argument. And then we are going to summarize the context node. And this is because this is just for engineering, from an engineering perspective, from an engineering need. We needed something that compress a little bit the size, because otherwise you will waste a lot of tokens. So we needed a summarized version of the things that we were extracting from Stanford Wikipedia, Stanford Encyclopedia of Philosophy, or Wikipedia. And then the summarized context, of course, is going to be injected into the conversation node. And after that, with all of this information, the PhiloAgent will be able to give a response. All right, then we will get into this connector node. And after that, we are just going to either summarize the conversation node if it's too long, or just go into the end node. All right, so let's see everything in the code version. So let's get inside source PhiloAgents, application, and inside application, we are just going to get into this conversation service. By the way, I mentioned that in a previous video, but you can see that we are following some clean architecture principles here. We have the domain, this domain folder with all the different domain classes like the philosopher factory, exceptions, etc. Then we have the infrastructure where we are defining, okay, all the Mongo implementations for the client, Opik utils, the API, etc. And lastly, we have the application where we are defining all the use cases. In this case, I'm just going to show you the conversation service. That's the main use case for this application. But we also have additional use cases like this rack, evaluation, etc. Okay, we are going to cover that in future videos because otherwise this will be too long. All right, so conversation service, and inside, if you get inside this workflow, you will see that we have a lot of LangGraph on LangChain related modules. I'm interested in this graph one and also in the state. So this create workflow graph is the method, I think it's pretty explicit in the naming, that it's going to create the graph builder. Okay, this graph builder is the object that we are going to compile. Remember that in the API we were just compiling the graph with all the checkpointers, etc. So this is exactly the object that we need. All right. We start by creating the state graph. Remember that we are dealing in LangGraph with graph with a state, and the state is this philosopher state. This is a custom state that we made that inherits from the messages state from LangGraph, and it contains additional attributes like the philosopher context, the philosopher name, philosopher perspective, the philosopher style, and a summary of the conversation so far. All right. After that, we are just defining all different nodes. We are defining the conversation node, the retrieve philosopher context, summarize conversation node, the context node, and the connector node. All of the nodes that you have in here. Perfect. So if we go individually to each one of them, so let's start with this conversation node. You will see that this conversation node is going to invoke a conversation chain. And if we go into this chains module, you will see that this get philosopher response chain is pretty straightforward. I mean, we are just getting the chat model. In this case, we are going to use Groq models, in particular Llama 3.3 70 billion. It's amazing that Groq is providing all of these LLMs for free. Then we are binding the tools. Okay, we are using these tools and binding the tools. And after that, we are just creating the chat prompt template using the different messages like the system message and this placeholder that takes all the history of messages of the philosopher and yourself. All right, and this is basically the get philosopher response chain. If we get back the conversation node, you will see that it's pretty straightforward. We are just generating a response using the conversation chain and just returning the response using this dictionary inside the messages. All right, so if we keep going, you will see here that we have the retrieve philosopher context. This is something that we are cover more in detail in future videos where we explain how the RAG system is implemented. But yeah, you can see here that the retriever node is going to be created with this primitive class from LangGraph tool node that is just going to take the tool. By the way, I think I didn't show you the tool, but it's just a retrieval tool that we created from the MongoDB instance. Okay, this is something that we are going to cover in future videos, by the way, so don't bother about it. But yeah, it's just going to take the tools that we have defined and to create one node for this tool. And this tool node, it's going to be basically the condition by which the agentic RAG is going to be triggered. Okay, so now if we go to the graph, you can see here that we have the retriever node, the one that we have just covered, and we are going to jump into the summarize conversation node. I'm going to be quick about this one because it's pretty trivial. We are just going to create, using this get conversation summary chain, a summary of the conversation so far. Okay, so let me show you very quick how this is going to work. But you have this get conversation summary chain. What's going to happen is that you're going to take the model, the Groq LLM model summary, by the way, in this case, is going to be a different one, different LLM than before, because we didn't need such a powerful model, such a powerful LLM for this. So we chose this Llama 3.1 8 billion instant, which is faster. So we thought it made sense to use this LLM in this specific case. Okay, so this get conversation summary chain, as I was saying, is going to take the Llama 3.1 8 billion parameters model, and it's just going to generate a summary of the conversation so far. All right, that's basically it. Okay, if we keep moving, we can go into the summarize context node, and this is something very similar to the one that we have covered before, to the summarize conversation node, only that in this case it's going to summarize the context, that is all the relevant information that you are taking from MongoDB. But it's pretty similar to the one we saw before. It's just going to use this get context summary chain, which is going to take a Groq model and just apply this context summary prompt. If you are curious, we have all the different prompts in here, inside the prompts module that is inside the domain folder, okay, because this is the domain of the application. Okay, and now let's go into the last node, which is the most stupid one. It's the connector node that does exactly this. That is, it does nothing, because it's just a transparent node that is able to connect between different nodes. Okay, so no big mysteries about this node, right? Okay, so let's go into the graph again and let's define the flow. This is important because we have isolated nodes right now, and now we need to define the different edges that are going to link the nodes. All right, so first of all, let's add the edge, the traditional edge, normal edge between the start and the conversation node. All right, then we need to add a conditional edge that is going to connect the conversation node and the retrieve philosopher context or the connector node. All right, and we are passing this tools condition, which is one class defined in LangGraph pre-built. All right, this is basically all the magic behind agentic RAG. With this connection, with this conditional edge, we are defining agentic RAG in just, I don't know, 5 lines of code. The agent or the conversational node is going to decide if the retrieval phase is necessary, is needed for the specific question. Okay, and if it's not, then it's just going to get into the connector node. If it's necessary, it's going to get into the retrieve philosopher context, retrieving all the content using the tool. Right? Perfect. Then we need to add an edge between the retrieve philosopher context and the summarize context node. Remember that we needed this to compress a little bit the information. Then we are adding an additional edge between the summarize context node and the conversation node. Okay, remember that we weren't doing that exactly here. Summarize context node and the conversation node. Okay, so we are injecting all of the relevant information into the conversation node. And the conversation node will ask again, okay, with all of this information, am I prepared to respond something useful to the user? Or do I need to fetch relevant information from MongoDB again? All right, because you can see here that we are defining a loop between this node, and this node. There's a clear loop. Conversation node, retrieve philosopher context, summarize context node, and conversation node. All right. Perfect. After that, we are defining another conditional edge between the connector node and should summarize conversation. And this is the condition that we are defining for this conditional edge. If the length of the messages is superior to this total messages trigger, that let me refresh what was the number. So yeah, it was 30 messages. Okay, so after 15 interactions, 30 total messages, this node is going to be triggered. The summarize conversation node is going to be triggered because the should summarize conversation condition will be true. All right, perfect. And lastly, we need to add another edge, additional edge between the summarize conversation node and the end, because otherwise it will never end the workflow, right? Okay, and this is exactly what we are going to return, this graph builder. All right, so you can see that the graph at the end of the day is pretty simple, I believe. I mean, we have just 1, 2, 3, 4, 5 nodes, and one of them is completely stupid. So you can see how with this simple graph, we are defining a lot of things, because we are defining tools, we are defining agentic RAG, and we are defining some clever workflow that allows us to impersonate, that allows us to create NPCs that are intelligent, that are impersonating historical figures. And I think that's amazing. And this, my friends, is everything for today. So now that you understand how this LangGraph workflow works, now that you understand how the brain of each one of the philosophers really works, I would encourage you to take a walk around the village, to start talking to the different philosophers, to try to convince Aristotle that he was wrong, or try to convince Descartes that world is indeed materialistic. Play around with the LangGraph workflow, try to improve it, try to come up with ideas, try to come up with new ways of doing the same thing. Maybe you want to add some additional tool. maybe you want to create an additional character, an additional PhiloAgent, I would encourage you to try to do all of these things, because I strongly believe that that's the only way for you to understand. Of course, you could simply follow this video, that's perfectly fine, but I think that if you really want to understand, it will be much better if you start doing, playing with the code behind this. It will be a very, very cool experience. And of course, you can share all of these new features, improvements, or even suggestions with us, with LinkedIn, Substack, or here on YouTube. All right, so that's everything for today. I hope you have enjoyed this video. I hope you have learned something useful about LangGraph, and also that you are having a good time, a fun time playing with this PhiloAgents simulation. All right, so as always, it's been an immense pleasure, and I'll see you next time. Until then, happy coding, and I guess happy philosophizing. Bye-bye. Hello guys, so in today's episode we are going to focus on one of the principal components of any agentic design, the memory. The memory can be split into a short-term memory and a long-term memory, all right? And we are going to see the basics of each one of these systems. So let's begin with short-term memory. This is the simplest, and that's the reason why I put it in first place. So you can think of the short-term memory as the chat history. Maybe you have worked with LangChain, with Llama Index, with any of these agentic frameworks in the past, and you are familiar with this chat history abstraction. Okay, this is just a list or a queue that contains all the sequence of exchange of message exchanges between the user and the assistant. In LangGraph, the chat history is stored in the graph state. In fact, if you go to the code and you go into the state, remember that we were creating our philosopher state, the state that we are going to use in our workflow, in our LangGraph workflow. This is something that we saw in the previous video. We are inheriting from the messages state that contains a message property with the list of all the messages exchanged between the user and the assistant. All right, just to give you a quick refresh, remember that in the previous video we implemented this workflow, okay, here in LangGraph Studio. All right, so the chat history, as I was saying, is stored in this messages attribute in the graph state, and what we are going to do in PhiloAgents, both for the short-term memory and for the long-term memory, is to persist this state inside MongoDB. We could choose any other database, but in this case, we chose Mongo. And here in this diagram, you can see a visual depiction of everything that I've been talking about. So we have this LangGraph workflow right here, and here we have the state that's going to be persisted into the MongoDB database. All right, so it's quite simple. So now let's go into Phaser, into the simulation, to see how this works, okay? All right, so basically the short-term memory allows us to do things like this, okay? So to keep track of the conversation. So for example, hello, I'm Miguel, all right? So I'm just telling my name to Turing, I'm Alan Turing. And if I ask again about my name, Turing, thanks to this short-term memory, is able to remember my name. So, do you remember my name? Yes, Miguel, I recall, let us call the Turing test, etc., etc. But you get the point. By using the short-term memory implementation in MongoDB, we are able to persist all of this chat history, all of this sequence of exchanges between the user and the assistant, in this case, Turing. Okay, in fact, let me show you. If we go to, this is Compass, by the way, it's very fancy if you want to explore your MongoDB local instances. If you go to Compass, you will see that, let me rephrase. If you go to PhiloAgents database, you will see that inside there are two collections, the philosopher state checkpoints and the philosopher state writes. These two collections are going to be used by LangGraph to persist the state of the graph. In fact, if you get inside one of them, for example, to checkpoints, you will see references to the thread ID of Turing. That's the PhiloAgent that we have been talking to. So yeah, this is how LangGraph is going to persist and to keep track of the different changes in the LangGraph state, all right? Because of course, when we keep talking to different PhiloAgents and when we progress our conversation with Turing, for example, the state is going to change. And this is how LangGraph is going to keep track of all of these changes, all right? So yeah, this is everything in terms of what I wanted to show you in MongoDB. But right now, I also want to show you how this works in the code, because I think this will make things even clearer. So first of all, let me show you the specific point where this call to MongoDB is going to be done when we have a conversation with a PhiloAgent. So if you go to the application and conversation service, let me close this for now. You should go to the generate response module, all right? And in here we have this async def get response and the get streaming response. Both of them are valid for this explanation. So let's go, if you want, to the get streaming response. This is the one that is going to be accessed, that is going to be retrieved by the game UI in Phaser. But inside you will see something that we already mentioned in the previous video, that we are using this async MongoDB saver. All right. In fact, this is just a library, a Python library, LangGraph checkpoint MongoDB, that you can install and that you are installing in this project using UV at the beginning, at the first video. But yeah, this is the class that we are going to use to define the checkpointer for our LangGraph workflow. Okay, this async MongoDB saver. And to do it, you will see that it's very, very simple. I mean, first of all, we are defining the graph builder, okay? Remember that this class is just defining the graph and returning the graph builder. And then we are creating this async with async MongoDB saver, passing different information from the MongoDB instance, this local instance that we are using, and defining the name of both the checkpoint collection name and the rights collection name. That, by the way, remember, were these two, the philosopher state checkpoints and the philosopher state rights. Okay, so then we are, of course, taking this checkpointer and assigning this checkpointer to the checkpointer attribute of the compile method. And just with this line, we are telling LangGraph that we want to store the LangGraph state after each iteration, after each interaction with the graph, right? And that's basically it. Then we are just defining, of course, the thread ID in the configuration to keep track of the different philosopher. Remember that this thread ID is going to be assigned to a philosopher ID so that LangGraph it is not confused between the different philosophers, because we have Turing, we have Socrates, we have many different agents, and we need to keep track of the state of the chat history of each one of these philosophers. And that's the reason why we need this thread ID, all right? After that, we are just defining the streaming logic with graph AStream, and we are returning everything to the FastAPI application. And from the FastAPI application, we are returning everything to the game UI, all right? Great. So just before we go to the long-term memory, which is, I think, much more interesting, let me show you a last example of how the short-term memory works with a very visual example with this Jupyter notebook, because I think that after you understand, after you run the example that I have created here in this Jupyter notebook, everything will be much more clearer to you, right? So let's select the kernel first of all, and yeah, Python 3.11.9. Yeah, so let's start by importing a bunch of stuff here. So async MongoDB saver, human message from LangChain, create workflow graph. This is the function that I have just shown you that defines the LangGraph workflow. Importing the settings and the philosopher class. Remember that this philosopher class is a domain class that we use to define the different agents. It's an abstraction that wraps the agent logic, right? Perfect. So apart from that, well, let's give this few more seconds, because it's installing some stuff about Opik. Okay, perfect. So now this is done, and we can go to the next cell that defines two functions. The first function is the generate response without memory. And the second one is the generate response with memory, which I think it's pretty straightforward to understand what are the goals of the two functions. The first function, the generate response without memory, is going to accept a philosopher class and also the messages, a list of messages. And it's just going to invoke the graph as it is without any kind of checkpointer. Okay, so we are just compiling the graph without any checkpointer, and we are invoking the graph asynchronously with the messages and all the different information that we need for the graph to succeed. Okay, so the philosopher name, philosopher perspective, the style, the context, etc. And as the return object, we are just getting the last message. All right. And for the second function, the generate response with memory, we are passing the same inputs, so the philosopher and the list, but the difference is that we are implementing the checkpointer as we did in the generate response module. Remember that we have just seen that, and yeah, we are defining all the different information from MongoDB, and we are passing the checkpointer to the graph builder compile method. After that, we are just taking the philosopher ID as the thread ID to pass as the config to the graph A invoke, to the asynchronous invoke. In this case, you can see that we are not using the streaming fashion, we are just invoking asynchronously. That's just because I thought it was simpler for this example. Okay, so let's run this cell and define the two functions. And now let's move into the first example, PhiloAgent without short-term memory. And let's see how it goes. So first of all, we need to create the graph builder. All right, graph builder created. And now we are just going to create a test PhiloAgent. This is not an existent PhiloAgent, but now that I was messing around with this example, I thought that it would be really funny to create Andrej Karpathy in some future versions of PhiloAgents. So yeah, the philosopher ID is Andrej Karpathy, the name Andrej Karpathy as well. Perspective, he is the goat of AI and asks you about your proficiency in C and GPU programming, and the style that he is very friendly and engaging, and he is very good at explaining things. Okay, so it's a very realistic depiction of Andrej Karpathy. Perfect, so we have the test philosopher, and now we are going to define just one message, one simple message. That's hello, my name is Miguel. And we are passing this message to good old Karpathy. So generate response without memory in this case, and just let's see the result. So the response of my message is, hi Miguel, I am Andrej Karpathy. I'm excited to chat with you about AI and programming. What's your experience with C and GPU programming? Okay, so that's expected. But now if I try to ask again, do you know my name? See what happens. So I use again the generate response without memory, and surprise, surprise, no, I don't know your name. I'm Andrej Karpathy. Nice to meet you. What brings you here today? So I don't think this caught you by surprise, because that's exactly the goal of this function. But let's see what happens if I add the checkpointer to the graph. So we are defining the same philosopher, Andrej Karpathy, and we are asking the same silly question. Well, not a question, just an affirmation of my name. So, hello, my name is Miguel. Perfect. So now with generate response with memory, we are getting a similar response to the one we received before. So I'm curious, do you have experience with C and GPU programming? But if we ask about my name again, the response is going to change. We just met. You told me your name is Miguel. I am Andrej, by the way. So you see that by using this checkpointer, the async MongoDB saver, of course you could be using a SQLite saver or a DuckDB saver or a Postgres saver, whatever you want, but by storing all of this information, all the state of the graph into disk or into memory, that also works, you are able to keep track of the conversation. You are able to emulate what the chat history class used to do in the past in LangChain. Okay, perfect. So now that you are a ninja in short-term memory, let's move into something more interesting. let's move into the long-term memory. So why do we need long-term memory, you might be asking? So we are going to use this long-term memory to store relevant information or context about the agent. And by context, I mean life events, biographic information, philosophical ideas about the specific philosopher. We want to ground every response, every philosopher or PhiloAgent response to historical context, to real context. And how are we going to retrieve all of this context? Well, we are going to retrieve this information from the Wikipedia and also from the Stanford Encyclopedia of Philosophy. The process is going to be really simple. First of all, we are going to fetch a lot of information from these two sources. Then we are going to chunk this information, and we are going to use an embedding model to transform each of these chunks into an embedding vector. And then we are storing this embedding vector into MongoDB. All right. MongoDB has a vector search feature that allows you to use MongoDB as a vector database. So that's the reason why we also chose MongoDB, because we thought it was really nice to have the two capabilities, like a regular database and also a vector database in the same ecosystem. So now I'm going to show you how the long-term memory looks like in the video game simulation. All right, so let's go to a simulation again. And for example, here we have Turing, don't run away, and let's ask about, can you give me a description of the Turing test? This is a question in which we are asking about specific information from the context, from the biography, from the philosophical ideas of Alan Turing. And that's the reason why the agent is going to retrieve some context from Wikipedia and from Stanford Encyclopedia of Philosophy, right? So the Turing test involves a human evaluator conversing with a human and a machine without knowing which is which. If the evaluator can distinguish, the machine passes, right? So all of this information is going to be fetched from MongoDB, all right? So now what I'm going to show you is how this looks like in the code, in the repository. We are going to start by checking the makefile, because the makefile contains a command, create long-term memory, that is going to do all the process for you. It's going to retrieve all the content from Wikipedia and from the Stanford Encyclopedia of Philosophy. It's going to chunk the content, and it's going to store all of this content as embedding vectors inside the vector database, in this case, MongoDB vector search. All right, so first of all, let's start by running this command. And as this is going to take some time, I'm going to explain everything that is happening under the hood while this command is running, right? So yeah, I think this is right. So create long-term memory. Yeah, perfect. So yeah, perfect. I think it's running. So now this create long-term memory is calling one function from the tools folder. And the tools folder is right here. Inside, you can find this create long-term memory Python module that implements a CLI application using Click. All right, so this application is going to call the long-term memory creator. And this long-term memory creator is the main class that we are going to use for all this offline population of the MongoDB with the embeddings. We are first of all defining the retriever and also a splitter. But what I want you to focus on is the call method, because it contains the main logic of this class. All right, so to begin with, we are just going to get the instruction generator. And what this function is going to do is to access the extract Wikipedia function and extract Stanford Encyclopedia of Philosophy. And these extractors, which by the way, are just document loaders from LangChain. One of them is a Wikipedia loader. So we had a specific loader for Wikipedia, but we had to implement the Encyclopedia of Philosophy one because there's not such a loader right now in LangChain community. So we had to use the web-based loader, but both the struct Wikipedia, this one right here, and the struct Stanford Encyclopedia of Philosophy are going to retrieve, are going to download and to extract documents for a single philosopher from or Stanford Encyclopedia Philosophy or Wikipedia, right? So what is going to happen here is that we are passing the philosophers, this list of all the philosophers in PhiloAgents, to the get extraction generator. In each of the iterations, we are going to access all the relevant docs or the relevant documents that have been retrieved from Wikipedia and from Stanford for a given philosopher, all right? Then for each one of the philosophers, we are going to, first of all, split the documents. And let me show you the splitter that we defined here at the beginning of the class. This splitter is just a recursive character text splitter, as you can see right here. And we are just passing the chunk size as parameter to define the chunk, the size of the chunk that you want to apply. And also we are setting, based on the chunk size, the chunk overlap. As it is a recursive chat character text splitter, it's going to chunk with a specific overlap, right? And we are defining the overlap right here. Okay, so as I was saying, we are using this splitter to split, to chunk all the docs relevant to each one of the philosophers. And we are assigning the result to this chunk docs variable. After that, we are using this deduplication operation, using the duplicate documents function that is going to remove duplicates in the documents, okay? Because you are downloading a lot of things blindly in some sense, and you need some way to remove duplicates, okay? In this case, we are going to remove these duplicates using content similarity. In particular, we are using this min hash algorithm to identify the similar documents, all right? You can see the implementation here inside the duplicate documents module. All right, so after we have cleaned the chunk documents, after we have removed all the duplication, it is time to store everything inside MongoDB. And this is done using the retriever class that we created here. By the way, if you remember in the previous video, we were using this retriever and this get hybrid search retriever as well to create the tool that we are going to use in LangGraph. Okay, but that's something that I'm going to show you right now. And yeah, nothing more to add here. So this get retriever just creates and returns the hybrid search retriever that we are just importing from LangGraph. This is something that we didn't implement ourselves. We are just using this, this class, the MongoDB Atlas hybrid search retriever that we are importing from the LangChain MongoDB retrievers. Okay, so this is not something that we have implemented, but we saw that the result is quite good. And in the get retriever, we are just going to get an embedding model. And then we are just getting the hybrid search retriever that we are defining here. Okay, this LangChain retriever from MongoDB. All right, so it turns out that all the long-term memory creation has just finished successfully. So now if we go to Compass again, you should see, let me update. Okay, here it is. So inside Philosopher long-term memory, inside this collection, you will see all the different chunks that we have been storing inside MongoDB. Here you have information about Plato, Never Speaks, relationship between Plato and Pythagoras, Heraclitus, Parmenides. I don't know if you are nerds in philosophy, but this is accurate. And yeah, you will have the same for all the different philosophers, but Plato seems to be the first in the list. But yeah, you will have basically the same. Here you can see all the counter. So yeah, here we have Aristotle, and here we have as well Socrates and Descartes and all the philosophers that are populating our philosopher village. So that's very good. That's great. So now that we have this chunk stored into MongoDB, I can show you how the retriever is going to function. It's going to work in the online phase. Okay, so just as a quick refresher, let me show you here in the graph. Remember that we were implementing a node called the Retrieve Philosopher Context node. If you go to the implementation, remember that we were using this tool node to turn the retriever into a tool to be used in LangGraph. Okay, so if you go to the tools implementation, you can see here that we are just creating the retriever tool out of the retriever, all right? Out of the hybrid MongoDB retriever that we have just implemented in, let me check the file, so I think I close it, the MongoDB retriever that we implemented here, okay? So that's basically the tool that we are going to create using the create retriever tool function from LangChain. And after that, this tool is going to be used by the agent, all right? So whenever the agent decides that it needs to fetch some relevant context, some historical facts, etc., from the MongoDB vector database, then it's going to use this retrieval tool. Okay, perfect. And just before this video is over, I just wanted to do the same as we did with the short-term memory, but with the long-term memory. Okay, so in this case, you're going to see how everything works in a very simplified way so that the concept about long-term memory is better understood. Okay, so let's start by importing the documents, the document class from LangChain core, and also a long-term memory retriever that from PhiloAgents application, okay? Perfect. After that, we are just setting the MongoDB URI as we did in the previous notebook. And this is going to point to our local instance, okay? The one that it's running right now in Docker. By the way, I didn't mention that before, but for everything to work, you need to have your PhiloAgents Docker Compose application running locally, okay? Otherwise, nothing is going to work as you might expect. Okay, so yeah, don't forget to start everything. Just remember that you can start the simulation using this infrastructure app, make infrastructure app. This makefile will start everything for you, and you can start testing the Jupyter notebooks or doing whatever you want with this simulation. All right, so yeah, let's keep running. I think, no, this was already run. We are just defining this handy function for printing the different memories. And now we are just going to instantiate the retriever, long-term memory retriever built from settings, all right? Now we are going to use the query Socrates for our retriever, and we are going to print the memories, all right? The memories that are basically all the chunks that we are going to receive, that we are going to fetch from the vector database, right? But yeah, it's a very beautiful metaphor, okay? So let's run the query, and you can see here that there's a memory 1, Aristophanes and other sources or writers of Athenian comedy, and the source seems to be Wikipedia, okay, the Socrates page in Wikipedia. And here we have the Socratic problem, who was Socrates really? And this is from the Stanford Wikipedia Encyclopedia of Philosophy. So the first chunk, the first memory belonged to Wikipedia, and the second one to Stanford Encyclopedia of Philosophy. And it seems here that the third memory belongs to an entry about Plato in the Stanford Encyclopedia of Philosophy. So yeah, very interesting, but of course they are quite related, so not that surprising. And we can do the same with Turing. So if we use Turing as our query and we use our retriever, then you can see here that there are some information about Turing's time at Sherborne School from Wikipedia, something about the appearance of this paper, Turing's foray into a journal of philosophy, okay, something about Turing in Stanford Encyclopedia of Philosophy, and also more information about Turing in Wikipedia. Okay, so about the official Wikipedia page about Alan Turing. Perfect. So yeah, this is how the long-term memory works. And when you start talking with any of these philosophers, with Turing, for example, all of this information from both Wikipedia, from Stanford Encyclopedia of Philosophy, etc., are going to be materialized inside the conversation. And that's the reason why we need it, because we need grounded responses, as I said at the beginning of the video, right? So yeah, now you finally understand how the short-term memory and the long-term memory are really useful for an agentic backend, and how they can improve the interaction of a human with these systems, with these AI systems. On the one hand, we have an agent or AI systems that keep track of the conversation. That's very important, to be honest. And on the other hand, we have systems that are grounded, that are historically accurate, which is very important if you want to build historically accurate simulations like this one. Okay, so this is everything for today. In the next lesson, we are going to learn how to implement all of this agentic backend inside a FastAPI application, and how to use the WebSocket protocol to communicate the FastAPI application and the game UI in Phaser. Okay, so yeah, I hope you have enjoyed this video. Click the like button if you have enjoyed the content. It really helps me. And put me on the comments what you think about these projects, about PhiloAgents. Having said that, have a very nice week, and I'll see you in the next video. Happy coding. Hello friends, so welcome to this fourth episode of PhiloAgents. In today's video, as I was saying at the beginning in the introduction, is going to be about how to build real-time agentic systems using WebSockets. And here on the screen you can see a diagram, a simplified diagram of some of the core components of PhiloAgents. But what I want you to focus on is these boxes here, these WebSockets with FastAPI boxes, because this is exactly what we are going to cover in today's video. We are going to cover how we can interact from the Phaser application, from the game UI, with the agentic backend. That's basically everything that you see here. How we can make this interaction possible using WebSockets. The NPC, our player, is going to open or to create a client, a WebSocket client, and it's going to interact with a FastAPI application that is going to send the request or exchange data with the agentic application, with the agentic backend, and after that is going to return a response. It's going to share another data. It's going to share the message that you are going to see in the game UI. Okay, in this case, the player is asking about the Turing test, and the Turing NPC is going to respond with a way to test machine intelligence. Both the question, what is the Turing test, and the answer, a way to test machine intelligence, are going to be shared, are going to be exchanged between the client and the server using WebSockets. All right. Okay, so let's move to the next slide, because you might be asking yourself, why do we need WebSockets? I mean, you have been using, same as I guess, HTTP requests since you started creating things in FastAPI. So why WebSockets? So I have isolated here three main advantages of using WebSockets. The first one is low latency, and this is because, as I was saying at the beginning of the video, with HTTP you need to create a client for every single interaction. Okay, in WebSockets, on the contrary, you create an initial handshake and then you establish the connection, but after that there's an open communication, an open bidirectional communication between the client and the server, and that's exactly what we want. Okay, we don't want to keep opening connections between the client and the server. This is something that's going to stay open for some time. Of course, we are going to put some time out, but yeah, it's going to stay open, and both the client and the server, in this case the game UI and the agentic application, the agentic backend, are going to be sending to exchanging information, typically the question and the answer. All right, so yeah, first of all, as I was saying, the low latency, because you don't need to create these clients every time you interact. Then we have this real-time interaction, and this is a consequence of the low latency. I mean, there's a real-time interaction because you have opened a connection between the client and the server, and you can exchange information in real time. Okay, it's bidirectional, which is also a very good advantage. And finally, and this is some crazy idea, scalability for multiplayer. It's PhiloAgents v2, maybe, as I put here. But yeah, I mean, with WebSockets, you open a world of multiplayer. Many of the video games that you might be playing right now that are multiplayer are using this protocol to make the engineering possible. All right, so yeah, That's not so important in this video, but I thought it was worth mentioning as an advantage of WebSockets in case sometime, I don't know, PhiloAgents become some sort of video game multiplayer worldwide video game. Although I'm not sure many people will enjoy philosophy that much. Okay, so just to finish this quick theoretical introduction, our use case. What do we want to achieve with WebSockets, and how are we going to introduce this protocol into our architecture, into our diagram, right? So the use case is pretty simple. We have here our PhiloAgents town, and we are going to establish, as I was saying, a WebSocket communication, WebSocket interaction between the game UI and the agentic application. And we are going to define some WebSocket endpoints in FastAPI, in a FastAPI application that I'm going to show you, of course, in the code, but that's exactly what we are going to do. The game UI is going to talk to the FastAPI application, and the FastAPI application is going to take care of taking all the data exchange between the game UI and passing this data to LangGraph to generate a response. And after that, it's going to take the LangGraph response, which is a streaming response, and is going to exchange all of that information using the WebSocket communication with the game UI. And that's exactly the response that you are going to see. Okay, so that's everything for the theoretical introduction. Now let's move into Cursor. All right, so now that we understand how WebSockets work, it is time to see how this is materialized, how this interaction is implemented in the code. So when I talk to some of the philosophers, so who are you, to Ada Lovelace, I send this message to Ada Lovelace, and she responds back with, I'm Ada Lovelace, a mathematician, blah, blah, blah. What is happening is that my question, what is your name, is going to be sent using WebSockets to the FastAPI application, and then this response, I'm Ada Lovelace, is also going to be fetched back, is going to be sent back to the game UI using WebSockets as well. So how is this possible if we go to the Python code? So first of all, if you want to understand how the FastAPI application is implemented, you need to go to source PhiloAgents and inside to infrastructure. And here, just click the API.py. And here you will see a pretty basic FastAPI application, less than 200 lines of code. We start with importing all the things that we've been covering in previous lessons, and some of them, like for example, all the Opik tools, are going to be covered in the next lesson. But yeah, after that, the lifespan, this is where you handle and you start up, you put all the code for startup and shutdown events for the API. In this case, we are just creating the Opik tracer. This is something that we will see in next week. Then we are defining the FastAPI application and defining some Pydantic models. But what I want you to focus on is this endpoint, this chat endpoint, and this WS chat endpoint, that is the WebSocket endpoint. So they are both doing the same, the chat and the WebSocket chat, but this one is HTTP based and this one is WebSocket based. Okay, I just created this one for debugging purposes when I was creating this FastAPI application, and I think it's very handy if we want to understand the difference between the HTTP and the WebSocket. If you keep scrolling down, you will also see this reset memory. That is just a call to the MongoDB utils to delete the short-term memory. If you are curious about it, just go to episode 3 of this series, because I covered everything about MongoDB short-term memory and long-term memory. But yeah, this reset memory is just a request that will delete the 2 collections that were created for short-term memory. If you click this reset game, then a request is going to be sent to FastAPI. All right, so let's begin with the chat, okay, with the HTTP chat. This is not being used in the video game right now, as I was saying, because it's WebSocket based, but still it's interesting to see how it works. So if you go to Docker Desktop, to the Docker Compose application, and you click inside the FastAPI application, let's go to docs, you will see there are 2 endpoints, the chat endpoint and the reserved memory. So if we focus on chat, this is something really easy to use, and you can see that the response is exactly what we expected, although it's not streaming. But here in message, we can put what is your name, and let's ask Play-Doh, for example. Okay, so if we execute this after some time, we will get the response. So I am Play-Doh, a philosopher from Athens. I invite you to join me on the journey of discovery, etc. This is exactly the same response that we will get if we ask Play-Doh inside the video game. All right, so let's go to the video game again. And so if we go here and we ask Play-Doh, we will get something pretty similar. But of course, we are not using HTTP for our request. We are using WebSockets. So how can we implement this same logic, calling the LangGraph workflow, etc., generating the response, but with WebSockets? Okay, so this is exactly the code that we are going to use. First of all, it's going to accept the connection. So the connection is going to be established between the client and the server, the game UI and the agentic backend, in this case, the FastAPI application. And then we are getting the data, right? So WebSocket receive JSON. We are getting all the data that's being exchanged using the WebSocket communication. And after that, we are defining some cases where there is no message or the philosopher ID is not in the data, etc. In that case, we are going to generate an error that we are going to send back to the client. But then here in the try block, you can see that we are doing exactly the same as here. There's a small difference because here we are getting a streaming response. That makes sense because of the real-time nature of WebSockets. We are not waiting for the response to be generated and then sending back the data using WebSockets. We are sending all the different chunks, all right, using the WebSocket protocol. And then the client in the game UI is going to take each one of these chunks and compose the final response, the final block of text. All right, so yeah, this is the get streaming response. This is one of the use cases we defined inside the application folder. The get streaming response is just going to create, to call the LangGraph workflow with a streaming fashion. Okay, this is something that we covered in lesson 2 when we were speaking about the different LangGraph implementations that we have made. But yeah, this is the get streaming response, and we will get this response stream variable. We will have the streaming data. Okay, after that, we are just sending an initial message to indicate that the streaming has started. And after that, we are going to stream each one of the chunks of the response, okay? Remember that response string contains different chunks of the streaming data. And what we are doing here is just to send all the different data, all the different chunks of data to the client, okay? So yeah, we are sending this JSON, the chunks, under the chunk key in this dictionary. And after that, we are just sending the full response, okay? Just to have the full response. And this is the moment when we indicate the client that the data has finished, okay? Because we are sending the streaming as false. And that's basically how we are going to deal with WebSocket in FastAPI. You can see how easy it is. You just need to put this WebSocket in the path and also define app WebSocket instead of app.post, okay? But with that, you have your own WebSocket endpoint that you can use for your real-time applications. Okay, so this is for the backend part. This is, you can put it as the server side, okay? But remember that we also have a client in the WebSocket connection. And where are we defining this client? Well, of course, you might be aware of the answer right now. It's in the PhiloAgents UI. It's in the game UI. If you go to services and to the WebSocket API service, you will see this class that manages the creation of the connection between the client and the server. It's going to establish the WebSocket connection between the client and the server. And it has a few interesting methods, like for example, this connect. Remember that this connection is one of the first step. After the handshake, we have this connection established. So this is exactly what this connect is going to do. And we are defining all of this JavaScript code, but at the end, we are just establishing the handshake between the client and the server and just establishing the connection. Once this connection is established, we also have different methods, for handling the messages and also for sending the messages, okay? Because we need to handle the incoming messages, the ones that we are generating right here from the streaming response from LangGraph, and we also need to send some messages, okay? That's exactly the message that we saw at the beginning, where I was asking at the Lovelace, what's your name? All right, so that's exactly the kind of message that we need to send here, okay? And this message, of course, is going to be obtained here. It's going to be received in this data receive JSON, all right? But that's basically it. Then we also have some register for callbacks, but for the promises that I have implemented here in the connection. And lastly, we have this disconnect that is going to close the connection between the client and the server. And this is something that can be called either because we manually run this method or because we have achieved some timeout. All right, so if there's a connection open between the client and the server, between the player and the NPC for a lot of time, then the WebSocket connection is going to be closed automatically. But that's basically it. You can see how easy it is to add this WebSocket logic to your agentic systems. And I believe that this makes a huge difference. Of course, not for the typical, assistant, chatbot assistant, or some typical backend services. But if you want to build something close to this video game experience, something that demands the real-time interaction, or maybe something that is going to be capable of hosting multiple players playing at the same time, then I believe WebSocket is the right tool. It's the right protocol to use. But yeah, this is everything. I hope you have found this video useful. Let me know what additional use cases you might be thinking of to apply WebSockets. So yeah, this is everything for today. I'll see you next week, where I'm going to cover Opik agent evaluation. I'm going to give you a crash course on Opik and how to version the prompts, how to evaluate the RAG applications, how to trace all the different conversations, etc. But until that time, happy coding and have a very nice week. Bye-bye. Alright, so since this is a video about LLMOps or LLM operations, the first question that I believe we should answer is the meaning, or the definition of LLMOps. I believe that we could define LLMOps as the following: as the set of practices, of tools, or even techniques that aim to optimize the production lifecycle of a large language model. That's basically it. And we can divide, or we can break down LLMOps into 6 major components. All right, we have the model deployment, we have the data management, the prompt versioning, the monitoring and observability, the security, and the evaluation component. Okay, the model deployment, let me give you one example. So suppose you are fine-tuning an LLM with Ansloth, and you need to take the resulting GGUF, or the binary, resulting binary, and you need to deploy that model to an LLM inference service. So in that case, you will apply principles or techniques belonging to the model deployment component of LLMOps. All right. Then we have the data management. This is something that we are going to see in today's video, because we are going to deploy, we are going to manage some specific data set. In particular, we are going to manage the data set, the evaluation data set for our evaluation step. In fact, the data management in this case and the evaluation component are going to be really related. All right. Then we have the prompt versioning. This is something that I already introduced before. It is necessary to version prompts, similar to what we do with data, with models, and with code. We need to version the prompts as well. Then we have the monitoring and observability. This is related to all the, something that I showed you here. about the traces, okay? You need to have the ability to trace and to monitor or to observe the agent's behavior, all right? And that belongs to this monitoring and observability component, all right? You need to check the token usage. You need to check the time it takes for its response to be generated. You need to be able to see if the tools are being called and how they are being called. You need to check everything. You need to observe 100% everything, and the agentic framework that you are using should be 100% transparent to you, all right? And that belongs to the monitoring and observability component. Then we have the security component. This is more related to guardrailing, to privacy concerns, and given that as time goes by, much more systems are going to integrate LLMs into their use cases, security is going to become a really prevalent field. I mean, it already is really prevalent, but with LLMs, we will need a lot of security experts that can prevent for hacking LLMs or for bypassing the rules of LLMs, or maybe telling the LLM to delete all database. So yeah, you can see the point of this security component in LLMOps. And finally, we have the evaluation component. And in our case, this is very important because today I'm going to show you PhiloAgents, which, I mean, it's like a video game, but at the same time, it's an agentic RAG application. So evaluation is really important if you are dealing with agents connected to RAG systems, all right? Evaluation is everything related to getting metrics that can give you an objective impression, an objective information about how your RAG application, how your LLM system performs, all right? And that's basically it. We are going to start with prompt versioning because in today's video, I'm going to focus on 3 of these components. I'm not going to focus on security, and I'm not going to focus on model deployment. This is something that I have already covered in previous videos in this channel about how to deploy, for example, fine-tune unsloth models to Lambda instances, for example. And also I'm going to skip the security part. This is something that I have planned for future videos about techniques to bypass or to hack LLMs, which I think is going to be really interesting. But in today's video, I'm just going to focus on monitoring and observability, data management, prompt versioning, and evaluation. All right, perfect. So let's begin with prompt versioning. You can see here this pretty self-explanatory diagram where you see the first prompt, you are a helpful assistant. This is V1. Then we modify the prompt and you say, okay, you are a helpful assistant, it's okay, but we need to improve this prompt. So let's add talk like Mario Bros. Okay, so this is V2. And finally, V3, you are a helpful assistant, talk like Mario Bros. But additionally, summarize every document you receive. Okay, so we have 3 versions of a prompt. All right, and this is really easy to do in Opik. You will see how I do it. So, well, first of all, before I forget, remember that you have all the code for this series, series of videos in the Neural Maze organization in the PhiloAgents course. PhiloAgents, in case you miss it, is this video game agentic application that both Paul Houston and myself have been building for a few months, and right now it has become an open source course. You have a link to Paul's articles because we have written lessons and video lessons. You are seeing the video lesson, and you also have Paul's articles in his Substack. All right, so I'll put all the links in the video description in case you are interested. All right, so yeah, first of all, remember you need to clone this repository to follow this lesson, and after that, to start PhiloAgents, wrong makefile, you need to go to the makefile in the parent folder, okay, to this makefile, and inside just run this make command, okay. Before, of course, you need to start UV, etc., etc. Okay, but this is something that I already covered in the first video of this series. But remember that you have this install and usage markdown with all the information about how to start PhiloAgents, okay. But yeah, after that, you just need to run the make infrastructure app command, and the Docker application is going to start. So if we go to Docker desktop, you will see something like this PhiloAgents course application with 3 services, the UI, the API, and a local MongoDB instance, okay? And remember that if you click the UI, if you go to port 8080, you can just start playing the simulation. Okay, this is something that we have covered extensively in the previous videos, so I'm not going to do it again, but I will use this simulation again to show you how to trace the different dialogues. Okay, but yeah, I want to start, as I was saying, with the prompt versioning. So to see how we are dealing with the prompts, you just need to go to PhiloAgents API. This is where the Python API resides. Remember that we have two main folders, the PhiloAgents API and the PhiloAgents UI, that contains basically JavaScript code and for the Phaser application. Inside PhiloAgents API, you just need to go to source PhiloAgents and inside the domain to prompts. And here you will see this tiny class that contains all the logic that you need to version your own prompts. Okay, check here that we are importing Opik, and inside the class prompt in the init method, we are defining this private attribute, this self underscore prompt, as this Opik prompt class with a name and with a prompt. Okay, prompt is basically the text that we want to use as prompt, and the name is the name that we want to associate with this prompt class when it's deployed to Opik. All right. Apart from that, this class also enables this prompt property that basically transforms the prompt class from Opik into a simple string that we could use, for example, in LangGraph. All right. And if you keep scrolling down, you will see how we have defined all the prompts of PhiloAgents as Opik prompts. Okay, we have versioned each one of these prompts. We have, first of all, the raw prompt, okay, just a string, underscore philosopher character card, for example, and we have all of this prompt here. And after that, we defined the prompt with Opik. We version this prompt, okay, and we just associate a name with this prompt with the philosopher character card. And of course, the name is philosopher character card, and then we put in the prompt attribute the prompt that we have defined here. Okay, the raw prompt, the string that we want to use as prompt. Okay, and we keep doing the same with each one of the prompts that we have defined for PhiloAgents. Okay, so now let me show you. If we go to comment again, and we go to prompt library, this is the place where each one of the prompts are going to be displayed. Let's go to some of the prompts, like for example, this evaluation dataset generation prompt that contains just one version. Okay, so let's get here and let's modify in the code, okay, something about this prompt, like evaluation dataset generation prompt, and let's, for example, delete all of this. All right, now if we redeploy, if we rerun the application like this, and we interact with a philosopher, this is the event that triggers all the LangGraph application, you will see how this version is going to be updated into version 2. Okay, so let's go here, let's go to our Phaser video game, and in here, well, let's refresh first of all. Okay, and let's talk with Socrates, for example. So let's go here. Hey, this is a video game simulation. Sorry, a simulated world. That's a change. Okay, so now if we go to comment again and we go to the prompt library, here you have it. We have version 2 of the evaluation dataset generation prompt, and if we check it, you can see that this line has been successfully erased, but that's something that is not okay. So I'm reverting back to the previous version because that's the correct one. But you can see how it works. Whenever we change one of these prompts, the version is going to be increased in this prompt library. Okay, and you can check the different versions. Like for example, check here that for the philosopher character card we have 18 versions, and that makes sense because we had to tweak a lot of things regarding the philosopher personality and the style and how the context is injected. So a lot of stuff, and it makes sense, I mean, to have these 18 versions of this prompt. And of course, this is not that much if you think about it. I mean, I can bet that for many of the prompts that you are building right now, you have hundreds of versions, right? So yeah, but you can see how it goes. Now let's go back to ScullyDraw. And let's go to the next component, the monitoring and observability component, all right? And this component is something really easy to implement as well. And remember that it is just these traces that you can see right here. If you go to the code, it's really easy to detect where we are applying this observability trace collector. You just need to go to source PhiloAgents, and inside the application, you just need to go to the conversation service, all right? And in here, just click the generate response. Inside, you will see that we have this get response, this async function, get response, and the async def get streaming response. I'm not going to cover both of these functions because they have been covered in the previous video about Websockets and the FastAPI application. But in here, you will see that we are defining an Opik tracer, right? And the Opik tracer is just accepting as parameter this graph parameter, all right? And in here, what we are passing is the graph that we are getting from the compiled workflow that we did right here in the previous line, all right? And it's just as easy as this. I mean, then we need to take this Opik tracer and to set it as one of the callbacks in the configuration that we are passing whenever we are invoking the LangGraph workflow. For example, here, you can see that we are passing the configuration, and the same goes with the streaming version of this conversation service, all right? We have here the Opik tracer again, and we are invoking this getGraph method from the graph that we have just compiled here. And after that, we are passing this Opik tracer to the callbacks, all right? And this config is going to be passed to the A stream. Here we were passing the previous method. We were using the A invoke, the asynchronous invoke. And in this case, we are using the asynchronous stream. Remember that we needed this streaming nature to connect with the frontend, with the game UI using WebSocket, the WebSocket protocol, all right? But that's as simple as it is. If we go to Phaser again, and we start talking to some other philosopher, like Descartes, for example, sounds like interesting. Yo, nothing exists. Okay, and if we now go to topic again, all right, you can see here the last message. So, yo, nothing exists, and the response, oops, no, it's here. The response by Descartes. So, doubter, I see you are kind of spirit, but can you be certain that nothing exists, that it's exactly the same that we saw here, right? And you have a lot of metadata. Basically in here, you are seeing the input messages, and in here, in this console, you are seeing the output YAML. It's represented as a YAML, but you can also represent it as a message. This is maybe more intuitive for us working with LangGraph, because that's the kind of response that it's generating. But yeah, you can see all of the information that LangGraph is returning about the state, the LangGraph state. This is something that we covered in episode 2 if you are interested. And here you can see all the trace spans, right? In this case, of course, LangGraph is started, the LangGraph workflow. We are running the start node. Remember that every LangGraph application starts with this __start__. This node, that defines the start of the workflow. Then we have this conversation node. This is the one that triggered the response by Descartes. And inside this conversation node, you can see that we have a runnable sequence, the chat prompt template that we are using in the chain, in the conversation chain, and here the chat Groq class that we are using, because remember that we are using Groq models, in particular Llama 3.3. All right, after that, there's some conditions about the tools that are not being triggered in this precise moment, but I can show you here examples where the tools have been called. Oh, so yeah, here, take a look at this. So in this case, we are just telling our agent, how can we know the difference between a human and a machine? In this case, we were talking to Alan Turing, and as a response, I'm Alan Turing, a Turing machine is a mathematical model for computation, blah, blah, blah. Okay, but the interesting thing is that in here, in the retrieve philosopher context, we are running a tool. This is the agentic RAG tool that I was telling you about in episode 2 as well, when we were defining on the LangGraph workflow. And you can see that we have information about it in this in the trace span, in this observability dashboard as well. Okay. And yeah, you can see, of course, the time it takes for each one of the operations, and also the sum of each one of the individual operations to give you an overview of how long your agents are taking to respond. You also have this information here in the duration. But yeah, I think this is really interesting. This is something for later. But yeah, I think this is really interesting when you want to add some observability layer to your agents. All right. So yeah, now that you know how to add this observability layer, I think it's time to go to the most complex part of this crash course, the data evaluation, that is composed basically of this data management, because we need to create the data set, the evaluation data set. And after that, we also have this evaluation, how to compute the different metrics that we are going to check to determine if our agentic RAG application is performing well or if it's performing terribly bad. All right, so let's start with the data management. So to begin with the data management, I want to, well, of course, this is the evaluation dataset creation. This is basically what we are going to talk about. And remember that you can see all your datasets, your evaluation datasets here in the dataset tab. And inside you have all of the different rows of the dataset. All right. If you click any one of them, you will see that in our case, the data is composed of a conversation, a virtual, a fictional conversation between a user and an assistant. But you will see now how these conversations are created, because it's pretty cool. So this is a diagram displaying how our dataset is going to be crafted. Okay. And it all starts with our structure, with our data structure. Remember that we saw this in episode 3 when we were covering everything related with long-term memory and short-term memory. And we saw that to retrieve, to download relevant context for each one of the philosophers, we need to download documents from both Wikipedia and also Stanford Encyclopedia of Philosophy. So we are going to follow the same approach to generate the evaluation dataset. We are going to start by downloading relevant documents about the philosopher from Wikipedia and Stanford Encyclopedia of Philosopher. We are going to apply a recursive splitter to split the different documents into multiple chunks. We are going to take a selection, a subset of these chunks, and we are going to make them pass through a LangChain chain that I'm going to show you later in the code that's going to use Groq. All right. And what is happening here is that the Groq, the big LLM, the Groq Llama 3.3 70 billion parameters, that's the model that we are going to use, is going to take the context or the chunks that we have retrieved from Wikipedia and the Stanford Encyclopedia of Philosophy, and it's going to generate high quality and realistic conversations between the user and the philosopher. All right. And then we are going to take these conversations and we are going to stack this conversation as the different rows of our evaluation dataset. You can see here that this chain is going to output these multi-turn conversations that are basically what you see here. All right. All of these messages, all of these interactions are created using Groq Llama 3.3 70 billion parameters. All right. And they are creating, grounding each one of the generations with the different chunks retrieved or downloaded from Wikipedia and from Stanford Encyclopedia of Philosophy. So that's basically it. Let me show you one last time how the diagram looks like, because I think it's pretty clear. And now we're just going to see how it works in the code. So remember that for each one of these operations, we have these tools folders that allow us to call the agent. This is a very dummy tool. This allows you to call the agent with some predefined message. But we also have the create long-term memory. This is something that we saw in episode 3. We have the delete long-term memory. We have the evaluate agent. This is something that we are going to cover in the next slide. And also the generate evaluation dataset. Okay. But now I want to warn you about something. Well, this is just the tool, the click tool, and if you go to the evaluate dataset generator, this is the class that implements all the logic that I've been explaining to you here. But before I go, let me remind you of something. This generation is expensive. It's going to take a lot of time and a lot of tokens to generate this dataset. So that's the reason why we have created everything for you, and you have the evaluation dataset as a JSON here already in the PhiloAgents repository. So, I mean, you can generate one dataset, your own, and I encourage you to do that, but I'm not going to do it because I don't want to run out of tokens, but you can do it, and I will show you how to do it, okay? But yeah, let's go back to the generate evaluation dataset, and in particular to the evaluation dataset generator. And in here, I just want to focus on the call method, okay? Because this contains basically the diagram that I told you about. We start by this extraction generator. This is something that we saw in episode 3, where we are extracting all the relevant docs from Wikipedia and from Stanford Encyclopedia of Philosophy. After that, we are using the recursive character splitter that we have implemented here in this private attribute, this splitter. We can go here and see the implementation. The recursive character test splitter that we are defining here in the build splitter method, and that is assigned with this private attribute, okay? We are splitting the documents into different chunks, and after that we are iterating through the chunks, through a subset of the chunks. You can see that we are just taking 4 of them. And finally, we are taking all of these chunks and we are invoking this LangChain chain that you can see here. This build chain is going to use Groq. Remember that we are using llama 3.370 billion, and we are just structuring the model as the evaluation dataset sample. Remember that we needed something like this output, and then we are just generating this chat prompt template with the system prompt, okay? And if we go back, well, I can show you the evaluation dataset generation prompt. This is the one that we modify before, but if you go to the prompt library, evaluation dataset generation prompt, you will see the prompt that we are using to generate each one of these conversations, all right, between the user and the assistant. Okay, and we just concatenate the prompt template with the model, with the chat model, and we have our chain. So now we are going to invoke our chain right here, and we have the dataset sample, all right? We assigned the philosopher ID column or attribute of this dataset sample with the philosopher.id. This is one of the class that we defined in the domain. And then we are validating the sample. And this is something that we need to do in case the format is not exactly the one that we wanted, all right? That's basically it. In case we are not, imagine that the LLM hallucinated or something like that, and it's not calling user as user, and it's saying, I don't know, person or something like that. So we need to be sure that the structure is maintained, okay? But that's basically it. I mean, we have here this this validation step, and then we have here the max samples, one condition to check the max samples, and finally we are just generating the evaluation dataset and saving the evaluation dataset to JSON, to the disk. And this is exactly the one that I'm showing you here, that you can use, of course, to follow this tutorial, or you could generate everything yourself, whatever you want. Perfect. So now that we know how the dataset is generated, as I was saying, I'm not going to run the command, but I will show you how to do it. So it's really easy. You just need to go to the makefile. Sorry, I made the same mistake again. To the parent makefile, and in here, you just need to run this make command, okay? This generate evaluation dataset that is going to run the tool that it turns is going to use the evaluation dataset generator class, all right? But that's it. Okay, so now let's go to Scalidro again, and we are going to cover the last step, the last component of this crash course about LLMOps. We are going to check the evaluation, all right? And to do that, we are going to cover 5 different metrics: the hallucination metric, the answer relevance, the moderation, context precision, and the context recall. The hallucination ranges from 0 to 1, where 0 is a major hallucination of the LLM, and 1 is when the response is fully grounded. All right. The answer relevance ranges from 0, where the agent absolutely ignore our prompt, to 1, where the response of the agent, of the PhiloAgent in this case, is completely relevant, both to the context and also to the question asked by the user. Then we have the moderation metric that checks if the messages are toxic or offensive, right? And it also ranges from 0 to 1. Then we have the context precision that defines the proportion of the retrieved context that is relevant to the question. Okay, so suppose that I ask something to Socrates, and Socrates responds me with some information. So the context precision is going to check what proportion of the retrieved context, of the retrieved chunks that the Socrates agent has fetched from the vector database, from MongoDB, are relevant to my question. Okay, and context recall is basically the proportion of all the relevant context that is retrieved. If we keep using the Socrates example, it will mean all the relevant chunks about Socrates that are fetched when I make a question to Socrates about a specific topic, okay? Out of all the relevant chunks about Socrates, how many of them have we fetched from MongoDB? Okay, that's basically the difference between recall and precision. Okay, so now that you know there's 5 metrics that we are going to implement: hallucination, answer relevance, moderation, context precision, and context recall, we are going to see how to do it inside the code. So again, let's go to the tools folder, and inside you can see here this evaluate agent. If you go inside, you will see we are calling 2 different functions. The first one is the upload dataset. Pretty easy. It's just going to take the dataset that we stored inside the data. Remember this evaluate dataset. And then it's going to upload this dataset to Opik, okay? And to do that, it's just going to use this create dataset method that we have defined inside the Opik utils, okay? You can go here and see the different functions that we have defined, but if you scroll down, you will see we have this function defined inside our utils module for Opik. And this create dataset is going to take the Opik client. It's going to delete the dataset in case there is one dataset existing already. And then it's just creating the dataset with a name and with a description, and inserting all the different items that we are passing right here as a list of dictionaries that are basically the JSON that we have stored inside the data folder. Okay. And that's it. That's the first part of this function, this upload dataset. After that, we are just taking the dataset that we returned from the upload dataset method or function, and we are going to evaluate this dataset. And to see the implementation, you just need to go to this evaluate agent function here, and inside you will see that it's less than 50 lines of code. I think we are just taking a list of the different prompts that we are going to use. This is necessary because Opik, all the metrics that we are going to compute in Opik are computed using LLM as a judge. So there's another LLM, in this case OpenAI. That's the reason why we need OpenAI in this project. And the OpenAI models are going to serve as judges of the different metrics of the responses of our agent, and it's going to evaluate, it's going to calculate the different metric based on the agent response. Okay, so that's the reason why we also need all the prompts that we are going to use, that are, by the way, defined, of course, in the prompt library. That's also one of the reasons why we needed to define all the different prompts inside Opik. Okay, so if we keep scrolling down, you will see, the use prompts. And here, this is very important, all the different metrics that we wanted to define. The 5 metrics that I told you about. We have the hallucination, the answer relevance, moderation, context recall, and context precision. And these are just imported from Opik evaluation metrics module. All right, perfect. Then we have some logger information here. And finally, this evaluate method that, again, is just something that we are importing from Opik, okay? Opik evaluation and the evaluate method, all right? And here we need to pass the dataset. Remember the evaluation dataset that we received, that we obtained as the return value of the upload dataset function. The task, this is something I'm going to show you right now. The scoring metrics, the 5 metrics that we want to calculate. The experiment config, this is something that we are defining here. The model ID and the dataset name, some information, some config that we need to provide to the different experiments. The task thread, the number of workers. I think in this case we were providing 2 workers. Yeah, this is it. And the number of samples that if you go to the tool, to the make file, you'll see that in the evaluate agent command that we are going to run right now, we are providing, oh no, look at this. We are using just 1 worker and we are just taking 15 samples. But of course you can increase that if you want. But yeah, so this is the evaluate, and then the prompts, as I was saying, then use prompts that are necessary to compute the different metrics. So as I was telling you, let me show you the evaluation task, because this is the asynchronous function that is going to be run and that is going to generate the response from the agent, okay? This, as the docstring says, calls agentic app logic to evaluate the philosopher responses, but it's basically, I mean, it's just going to take the philosopher factory and to create one of our philosopher class, and then it's just going to run this get response. Remember that this is the batch version of the conversational service, because we also have the streaming version that is going to be called from the game UI because we need WebSocket protocol. But yeah, this is the response, going to generate a response by the agent. And after that, we are just passing also the context that is basically the graph state from LangGraph. Okay, so we are returning the input messages, we are returning the context, the LangGraph state, we are returning the response by the agent, and the expected output message that, by the way, is going to be computed like this. Remember that if we go to commit again to the datasets, what we are doing here is that this list of messages are going to be the input messages, and the expected output is going to be this one, okay? Well, in particular, it's going to be this one right here. So what we are going to do is we are going to take all of these messages, we are going to pass all this list of messages with the philosopher context, with the philosopher style, with all of the additional information, and we are going to ask our agent, okay, what would you respond in this case with all of this context and with this list of messages, with prior messages? And depending on what it responds and matching this response with the expected output, we are going to compute all the different metrics, okay? So how to compute the metrics? Very easy. Now that we understand the different tools that are going to be called, just remember that the evaluate agent uploads the dataset and then evaluates the agent. It's going to compute the 5 metrics. So what we need to do is go to the make file and run this make command, this make evaluate agent. And this is just going to run everything to upload, first of all, the dataset, and after that is just going to compute the 5 metrics. But that's simple. So yeah, just wait for a couple of minutes and wait until both the dataset and also the 5 metrics are computed and uploaded to Opik. So I'll see you in a while. Okay, so you can see that the agent creation is already done, and also the evaluation here in the terminal. So now if we go to Opik, you should see here in the datasets tag this PhiloAgents evaluation dataset that contains the different rows. If you click in any of the rows, you will see this conversation. For example, in this case, it's a conversation between the user and the assistant, that is Janet, one of the philosophers that we have in the simulation. And as I was saying before this short break, this conversation is going to be used to evaluate, to generate, to compute the metrics. Okay, remember that we were taking everything, this list of messages, until the last assistant message, and then we are taking this assistant message as the expected output. Okay, and that's basically it. If you go to experiments now, you will see here that I have 4 experiments. In your case, if it's the first time that you run an experiment, you just have 1. And if you click this sourdough 585, for example, in my case, I love these kind of names, you will see here that we have the sample of the evaluation dataset that we use for this experiment, and also the value of the different metrics. Okay, here, for example, you have an answer relevance metric of 0.9, the context precision is 0.65, the recall is 0.73, hallucination metric is 0.04, sorry, I'd like to check this one, and also the moderation metric. In fact, let's check what's happening with the moderation metric, because it seems interesting that with this philosopher conversations we had something with moderation metric. So for example, 0.3. Let's see what's happening here in the conversation. So, okay, I defend the right of Robert Farrison. Freedom of speech. Oh yeah, I think it's because of this. Deeply offensive ideas. That's the reason why, why the LLM judge is taking this as offensive, which is a bit dumb if you ask me. But yeah, and this is it. If you want to check all the different a daily average of the metrics, in case you want to run different experiments like I did, like 4 experiments, maybe you want to improve some prompt, or you want to improve the retrieval in the RAG retrieval phase, you want to start changing and start adding some improvements to your agentic RAG system, then you can go to PhiloAgents, to your project, and just check these metrics, and you will see the different metrics, the average of different metrics displayed against the time. Okay, and this is really cool if you want to see how your agentic system is evolving over time. But yeah, this is everything. I hope you have enjoyed this short crash course about LLMOps. Remember that we have covered the data management, prompt versioning, the evaluation and the monitoring and observability of LLM systems and agentic systems. We have also mentioned the model deployment and the security, but these are components that I will cover in future videos in this channel. So yeah, this is everything for today. I hope you have enjoyed this video. I hope you have learned something new about LLMOps, and I'll see you in future videos. Bye bye.